What is going on, everyone? Welcome back to the channel. I hope that everyone's having an awesome day. In today's video, we'll be going over Autolykos, the Ergo proof of work scheme. It's going to be a pretty lengthy video, so grab a seat, grab a beer, enjoy, and let's get into it. Alrighty guys, so if you're not familiar, Autolykos is the Ergo proof of work scheme, algorithm, consensus protocol, and a good place to start reading about it is the white paper. So we're on Autolykos version 2, but when reading through the white paper, you might get a little confused. At least when I was first looking at this, I was like, what the hell am I reading? We've got all these algorithms, all these symbols, and a lot of computer science is involved, but I mean, it is feasible to understand. And in this video, my goal is to sort of explain to you guys how it all works, because for me as a miner, it's quite easy to set up a rig, but then it's a bit more challenging to actually understand what are my GPUs doing, like what are they computing. So that was sort of why I wanted to learn about all this stuff, because now you can get a sense of, is it ASIC resistant, is it memory hard, is it efficient, that kind of thing, and we'll be answering those questions in this video. So yeah, I'll link all the resources in the description. I think a good way to sort of go about this video is starting off with sort of a whiteboard vibe. It's my first whiteboard video, I guess, but it's and probably a lot of you won't be really interested in it, to be honest. But I think it is important for those interested to sort of get a grasp of how Autolykos exactly works. And a good way to do that is to first start off with proof of work schemes that we're familiar with. So starting off with Bitcoin, then discussing Ethereum, and then finally discussing Autolykos, and how Autolykos sort of innovates and builds on the limitations of Bitcoin and Ethereum. So let's get straight into Bitcoin. Bitcoin's a pretty simple proof of work scheme. I think we're all quite familiar with the Bitcoin proof of work scheme. Essentially what you're doing with the Bitcoin miner is the miner will fetch all the block data for the candidate block, and then in that block obviously you have data such as the hash of the Merkle root, the timestamp, the nonce value, the hash of the previous block. And what the miner essentially does is trials a bunch of nonce values, guesses, takes the hash of all that data, and then if the hash is below the target, and I believe it's a double hash, and it's obviously the SHA-256 hash function, and if that hash is below the target, then the miner is successful, propagates the information to the network. If it's a valid block, they're rewarded in Bitcoin. So quite a simple algorithm. The one thing I do want to point out is that this mining procedure is purely based on the speed at which a miner can compute the SHA-256 hash function. The faster the miner can compute the function, the more Bitcoin they can essentially mine. So this is interesting because we've had a lot of new hardware being introduced that just speeds up the process at which the SHA-256 function can be performed. So that's why we have something that you are probably all familiar with, ASICs. So as we see here in this graph, started off with CPU mining, then GPU mining, and then eventually ASICs entered the scene. And as you can see, it's a logarithmic chart. So I mean, as ASICs came on board, I mean, difficulty absolutely mooned. And that's not the kind of moon we want. And it's also not great for the network, and for the following reasons. So I've just done a couple notes here. So what's the problem with ASICs? I mean, it's essentially a barrier to entry. Where am I going to chuck this? So it's a barrier to entry, and why is it a barrier to entry? It's expensive, right? So if you're mining Bitcoin and you're originally using a GPU, but then you can't really afford an ASIC, because ASICs are a lot more expensive than easy to get hardware like GPUs or CPUs, then you're not going to be able to mine Bitcoin. The whole point of Bitcoin, though, is that it's decentralized and that anyone can sort of join the network if they want to contribute, right? That's why initially we had CPU, GPU mining, so any average Joe can just go off to the store, buy a GPU or CPU off the shelf pretty easily, and then start contributing. The issue with ASICs is that it's expensive, first of all. So if you want to get an ASIC, you need the amount of money first. The second thing is geographical limitations, right? If you're in a place and you want to mine Bitcoin, you have access to GPUs, CPUs in stores, but there's no access to ASICs or ASIC shipment to you, then you're not going to be able to mine Bitcoin. So again, it's a barrier to entry. And then you're also dependent on ASICs for Bitcoin mining, for instance, right? So if ASICs are out of stock, what's your alternative? You don't have an alternative, because if you go and buy GPUs and start mining Bitcoin, you're just outcompeted by ASIC miners. So there's no actual point of even buying a GPU or CPU to mine Bitcoin. So you're really dependent on the stock of ASICs. So that's the result of ASIC mining, and that's why we have a lot of focus nowadays on proof of work schemes that are ASIC resistant, right? Because we don't want these limitations that can jeopardize the security, jeopardize the democracy, jeopardize the decentralization of the blockchain we're using. So that's starting off with Bitcoin sort of in a nutshell. I would definitely look into Bitcoin if you're not familiar with it in terms of the proof of work and how mining works. But yeah, that's that. So then what happens is Ethereum comes along, right? So Ethereum is sort of what we're discussing next. And Ethereum basically comes along and says, let's not limit the speed at which one can mine on the speed at which one can compute a hash function. Instead, let's limit the speed at which one can mine on memory. So why is that such an interesting premise? Well, basically, with Bitcoin mining, as we mentioned, there was no hardware that was optimized to hash as fast as possible. That hardware was created, ASICs were created to do such a thing, and then we had all these issues because they're expensive to get, you have all these barriers to entry, right? So what Ethereum wanted was memory to be involved. So that's why you have sort of memory hard functions, as we like to call them, which are memory bandwidth limited, right? So let's go ahead and understand how this works. And just a quick sort of good read that I'd recommend is a Hashimoto paper, which sort of goes through why memory is a good place to start. All in all, it's because memory had years of research, billions of dollars of research, because all our devices, use memory at a large extent, and thus we've already invested as a society millions and billions of dollars in time into optimizing memory to a large degree. So that's why that's the premise for involving memory instead of a hash function, which can be much more optimized, right? Because if you have great memory that's already being developed, then you're not going to have some random supplier like Bitmain or innately that can increase and further optimize memory, because it's already pretty much already fully optimized. So now I have Ethash. Let's quickly go through how Ethash works. You have a sort of similar start to Bitcoin with a sort of block header, a nonce, and then you enter a function, which is a hash function. So the output is a hash, and then in this case it's the hash is mix 0. Then what happens? This is where it gets interesting. Based on the value of the hash mix 0, a DAG will be involved. To put it simply, a DAG is just a data set, right? It's an acyclic data set, but I'm not going to go into that. It's actually quite difficult. I still don't understand how a DAG is generated, but I sort of get how it works. But essentially, let's treat it as a data set. But based on the hash output, the value of the hash output here, mix 0, a specific DAG page is fetched. What does that mean? It's just simply fetching specific data from the data set. The reason why a DAG is acyclic is that if you have point A to point B never reverts back to point A. So it sort of goes off on its own path, and it's pretty much impossible to predict which data leads to different data points, because it's in the form of a DAG rather than just linear data. So I'll leave it up to you guys if you're interested in that to check that out. But what's interesting here is that you're basically, for every mix, in this case for Ethash, you're fetching memory. So that's why it's memory bandwidth limited. And then if we go on to mix 1, you basically have a mixing function again, which mixes the previous mix and the newly fetched data, and then it creates mix 1 in this case. What happens then, based on the value of mix 1, you have another data fetch, which is another DAG page, and then another mixing function occurs. And this keeps happening, I believe, 65 times, something like that. But now you can kind of see for every nonce what happens. Well, this is where this part is quite important. For every nonce, there are 64 mixes, and this means 64 memory fetches and 64 hashes, right? So why is that important? Because basically with Bitcoin, for every nonce test, there is no memory fetch. It's just a simple loop of a hashing algorithm, which an ASIC can do very fast. In Ethereum terms with Ethash, for every nonce tested, you have 64 mixes, which means 64 memory fetches as well as 64 hashes. What's the reality of this? So the reality is that we now have ASIC miners, I believe introduced in 2018. So the reason why you have ASIC miners, and the problem, you have the same problems with ASIC miners on Ethereum as you do with Bitcoin, and that's not great, right? So that's why a lot of miners are sort of in favor of moving to proof of stake, and Ethereum has come out and said they're not really going to work on a new consensus. They're focusing all their efforts on proof of stake rather than implementing a new proof of work function. So you might ask why. Well, you thought Ethash was memory hard, so how can ASICs be developed? Well, the reality is that, as we mentioned, for every nonce test, there's still 64 hashes being done. While there are 64 memory fetches, there's still a lot of optimization that can be done for increasing the speed at which all these SHA-3 like functions take place, right? So ASICs just optimize the speed and increase the speed at which all these hashes take place, but the memory speed, the memory fetches, the speed of that is basically the same as a GPU, right? Because it's using, as we mentioned, optimized memory, which is DRAM, which is used by pretty much all memory in our devices to an extent. But then we have the same result at the end of Ethash. If the final mix digest, which is based on all of these mixes and memory fetches, is lower than the target, we have a success or fail. So the beginning and the end of Ethash are quite similar to Nakamoto proof of work or SHA-256 proof of work, whatever one may call it. Alright, cool. So that's basically Ethereum and Bitcoin mining. What's a limitation? Well, there's ASICs involved. We don't want ASICs because of these barriers to entry, right? We want a decentralized network as much as possible. So now we introduce Autolykos. So that was a very long intro. Sorry about that, but I think it's necessary to go over all of that to first understand why Autolykos is important and innovative. So first of all, this is a brief description of Autolykos. So what does this mean? Asymmetric just means it takes a lot of effort to find a solution, find a proof of work, but it's very easy to verify because you just backtrack it, right? So asymmetric also applies to Bitcoin and Ethereum mining, so that should all make sense. Then memory hard, we just mentioned it involves memory in the proof of work process, and then it's a memory puzzle. I think memory here is redundant, but it's a puzzle, right? So it's a algorithm protocol, one or the other. So what is the summary of Autolykos? Well, we've got a quick summary here. In summary, the miner is tasked to find k equals 32. Let me get a finer line. The miner is tasked to find k, which is equal to 32 out of n elements, such that the hash of the sum of the elements is less than the target. So this might be confusing at first, but what I'm going to try and do is just break down Autolykos line by line and involve some of the stuff from the white paper as well as a graphic that I created to explain Autolykos. Cool. So let's start off with n. What is n? So n is very important to understand because just like we have a DAG in Ethereum, we have a data set being stored by the GPU in Autolykos, right? Because that's what's stored in memory, and that's how we're involving memory. That's why it's memory hard. So n is, well, let's put equals stored. So it's the number of elements stored by the GPU. What does that mean? If n is equal to 1,000,000, then the GPU has to store 1,000,000 pieces of data that are utilized in the proof of work algorithm, right? Say if n is 10,000,000, then the GPU stores 10,000,000 pieces of data. So you might be asking, what are those pieces of data? If n is equal to 10,000,000, what are the 10,000,000 pieces of data that we're going to store? So let's get into that. So that is what we call list R. This might get a little confusing, but I think it should all make sense. So what is list R? List R is n elements long, as we mentioned, right? Because it's the GPU stores n elements of data, and we can write these values as 0, 1, 2, 3, small lowercase r, up until, you guessed it, n minus 1, because we have n elements of r values, which, together make up list R. So now the question is, how are these values calculated? R0, R1, R2, R3, etc. How are they calculated? And I just want to revert quickly to these images here. So we're not going to worry about algorithm 3 or 6 just yet, but we want to focus on algorithm 2. This is essentially, if you understand algorithm 2, which involves these other algorithms, then you understand Autolykos, because this is literally just exactly what a Ergo miner does when mining a block. So first we have the input, which is the upcoming block header hash, much like in the case of mining Bitcoin and Ethereum. We have these inputs, the upcoming block header hash, and the block height, right? So M and H. So now we're on sort of line 2 already, where we're calculating all of these R values, right? Because we want to understand what is actually being stored by the GPU, n elements of R values, but what are these R values? And that's what we're going to go over now, and line 2 explains how these elements are calculated. They're calculated using this function here, as we can see. Cool. So this might be like, what is going on? You might be very confused. And let's just say we're calculating the first element of list R, which is R0. Let's just say we're calculating R0, right? Bring this down a bit. So we're calculating R0. How's that calculated? So we can see here R, and we're calculating R0. I mean, that should be quite clear. R0. So we're doing this function here. So what exactly are these variables? So we start off with brackets, as we all know. And we start off with this inner bracket of hj, well, the hash of j concatenated with h concatenated with m. But you might be asking, what is m, first of all? Uppercase M. M is constant data. It's 8 kilobytes of constant data, and that acts as padding, because by adding this padding in, when doing a hash function, it is slower for hardware like ASICs to create these hashes, because you're involving a lot more memory in the hash, so it slows down the speed at which the hash can be computed. So you're involving M, which is always constant. So don't get confused with uppercase M. It's just always constant, 8 kilobytes of data. H is block height, as we defined here, so that we don't need to define. We have J then. So what is J? Well, J is in the range of 0 to n. So J could be, if n is equal to 1,000,000, J could be 69, J could be 363,500. It's just in that range of 0 to n, and we'll see why in a second. So then what happens? Well, we have H. So what is H in this case, right? So we understand M, H, J. What is H? Well, H simply takes these inputs, which we've discussed, and passes them into a hash function. So capital H just says hash function. But what hash function are we using here? Well, we're using algorithm 3. So as you can see here, you have the H input, which is the hash input. So I'm not going to go into details regarding algorithm 3. You're involving Q, which is prime order of a cyclic group, and you mod by that value, right, as you can see here. But all I really want to discuss for algorithm 3, the only thing you really need to understand to get a grasp of what's going on, is that a hash value is returned. A hash value that's mod Q is returned, but let's forget about that. Let's just say a hash value is returned, right? So what you're essentially saying here is you're passing these values here into the algorithm 3 function, which is based on Blake 2B256. We'll get into that later. And you're returning a hash based on these inputs. So quite simply, just like any other hashing algorithm, that's what you're doing. The important thing about a hash function is that you are, especially in this case, because it's 256, you're returning a 256-bit output, which is 64 digits long. Each digit is 4 bits. And then that's 32 bytes long. That's important to understand for the next part. So again, I was pretty confused with all that because I didn't study CS, but it makes sense. I'd definitely look into that if you're a bit confused there. But now we have this part here. So we've discussed what happens here. We have a hash function that goes to algorithm 3, which returns a hash given these inputs. And then we have this take write part. So what is going on here? Take write 31. And what's happening here is, let's do an example. So let's say we're calculating R0, right? So for R0, what do we have? So let's just say this is what we're doing. So this is some definitions we covered. And then what do we have? We have take write 31 of the hash, the returned hash, right? So what's all that's happening here, and let's say the returned hash, as we mentioned, is 64 digits long, but let's say it's equal to something like this, and this continues for 64 digits, right? So as we mentioned, each of these digits is 4 bits, 2 of these digits is 1 byte, right? Because 4 bits is 2 times 4 bits is equal to 8 bits, 8 bits equals 1 byte. So all you're saying here is take write. You're saying take the 31 bytes on the right hand side of the returned hash. That's all it's saying. In other words, you're dropping the most significant byte, which is on the left hand side, because as we know, the returned hash is 32 bytes long, and then we're cutting it to 31 bytes long by removing the byte on the left hand side. So in this case, you'd actually be removing A5. And when you remove A5, this is what happens. You're left with 31 bytes, which is equal to this thing here. So R0 in this case, we could say R0, you could say the returned hash, let's just say the hash function was J was equal to 0, because in this case, we're doing it for R0. The height is equal to whatever the blockchain height is, and then we have constant data. So then let's say that returned hash was this hash. And then we have, obviously, the take write function, which cancels out the byte on the left-hand side and returns the remaining bytes. So now we can see actually what each of these values are, R1, R2, R0, R1, R2, R3, until Rn minus 1. We just keep doing this. And all that's happening is J is going from 0 to 1 to 2 to 3 to 4 for all of the R values. That should make sense, right? So it's actually very quick. It takes, just a few seconds to calculate the entire data set given n, because all you're doing is doing a bunch of hashes, and just adding 1 to j. It goes from 0 to 1 to 2 to 3, and you're just processing all these hashes. So that should all make sense. And I think what's important is maybe to look at a quick spreadsheet that I made, but basically you can predict, so given the block height, an n value is given, and it is set, you can read in the white paper that before block 614400, the n value was this, and then what happens to n is that every 51,200 blocks on Ergo, n increases by 5%. And this is important because the data set is increasing as the blockchain and proof of work gets longer and longer. So what you can do is actually predict for every block height the value of n, and since we know that each R value is 31 bytes long, all you do to calculate the entire size of the data set is the n value times 31 bytes, because each of these R values in list R is 31 bytes long, right? So then what you basically have done here is quite simple. It's just n value times 31. You get the size of the data set in bytes, and then you can get the size of the data set in gigabytes. So you can actually forecast the size of the data set given the block height, and that's important for GPUs because this is stored in RAM, right? So if you have, for example, a 4 gigabyte RAM, well, then you can actually forecast when that 4 gigabyte RAM or 4 gigabyte GPU will be out of date, because the data set size will exceed the amount of memory you have available in RAM. So that should all make good sense, and now we sort of understand what the GPU stores in memory. So obviously in Ethereum it was a case of the DAG, but in Ergo it's a case of, it's not a DAG, it's sort of like a data set determined by n, so it's n values long, and each R value is 31 bytes. So that should all make good sense. So that's the first thing a miner does for every new block. They calculate the data set, because as you can see, that's an input, right? If h changes, then you have to recalculate the entire data set. But that can be done in seconds, like we mentioned, because all it's doing is taking j plus 1 plus 1 plus 1 plus 1, and it does it until from j is equal to 0 to j is equal to n minus 1. So now we actually get into the proof of work process, what actually happens. And I'll go to the graphic in a second. What we've covered right now is we've covered this, which is basically sort of the mathematical way, very simple mathematical way. I'm not a mathematician at all. Like this is my extent of math, but I've tried to put in a simple way here of list R and what list R contains basically, and calculating list R, which we just did, is here. Instead of writing take write 31, you can just write drop MSB, drop most significant byte, which is on the left hand side, right? Cool, so we've covered that now. So now we have the data set stored in the RAM, but what is the actual proof of work? Well, while true, what do? We calculate the, we give a random nonce value, and then what happens once we have a random nonce value, the guess value essentially, is we have line 5 and 6, and these are what I sort of see as seed functions, I guess you could say. So, and this is where we sort of enter this part here, right? So we enter line 5, we're calculating I. So how do we calculate I? We take the nonce, and we take the upcoming block header hash M, pass it into algorithm 3, as we said, returns a hash value that is, in this case, it is 256 bits long. And then what do we do with that 256-bit hash? Well, we take the 8 least significant bytes. So we take that returned hash given the inputs M and nonce, and we take the 8 bytes on the right-hand side. So that should all make sense because we sort of discussed take write and the hash function. And then what we do is we mod by N. So what is this doing? Well, given these values M and nonce, we're hashing that, returning a hash, taking the 8 bytes on the right hand side, and then we're modding by N. So we're returning I, which is an integer in 0 to N. So then what happens is that I value is seeded into line 6, which calculates an E value. And this might be like, why are we calculating all this stuff? But it will make sense. So now we'll calculate E. What happens with E? Well, pretty much the same thing without mod N. We do H, the hash function given I, which we just calculated, the block height, and the constant data set. M, we pass it through algorithm 3, which is here, and then we return E, but in this case we're returning E, which is 31 bytes long, right? So we're returning a 31 byte hash, which is E. So now we've sort of created, with using the inputs, sort of a seed that goes into algorithm 6, which is index generation. And this is where it gets a bit challenging, because you can sort of follow along with what's been going on, but then it goes into line 7, which is index generation. It's like, what is an index? Like, why are we calculating indexes? And this is honestly like awesome work by Ergo, because I think it determines, as we'll see, which data is fetched from memory. So we pass to the generation indexes function, E, which we just calculated basically like a seed to this, M, which is equal to block header hash, and nonce, right? So as we can see here is what we do. So I'm not going to go too into depth in algorithm 6, which is here, but this is what we got, this is what we passed into the function. What do we do? I'm just going to focus on the diagram here. Essentially what we do, and if you want to really get into depth and understand the code, you can contact Wolf9466 on Discord. He's an absolute boss at this, and he helped me a lot with understanding how it works and providing a Python script. But all that happens here is when you're passing in these values into the index generator, is that simply put, a hash is created, a Blake2B256 hash is created with the seed, and the seed is these inputs. An extended hash is then created, which is it's basically just extending the current hash by itself, concatenating part of it. So as you can see, concatenating the hash and slicing the Blake2B256 hash with these inputs. And then what happens? This is the interesting part. So now we have a hash value that has been created, and we've extended it by a bit. And now we're slicing that hash to do what exactly? Well, to return 32 values, because k is equal to 32. If k is equal to 64, then 64 indexes are generated, but in this case, k is equal to 32. Return 32 indexes that are all mod n. So it returns 32 integers that are all between 0 and n minus 1, because they were all modded by n. All of the slices were modded by n. So that's why it's super interesting, because all of the nonce value and all of the data given these inputs, you're basically creating I, which seeds into E, which seeds into J, which then, depending on all those previous results, you generate a certain, you generate 32 indexes, but you kind of pre-predicted these indexes, right? You have to go through the process of creating I and E. So then this is what's super interesting. I mean, so we've sort of covered this. And 32 indices are returned. We don't really need to go over this. This is just if list R is created on the fly. But let's say, for example, and this is, if it's confusing, I think it helps to look at an example. Let's say you have index 0, and as we mentioned, it's a value that's mod n. So if n in this case is equal to, let's just say, I don't know, as we see here, n is equal to 67 million, which is equal to 2 to the power of 26. So all of these values returned by the index will be within this range, right? Because it's mod n. So index 0 is equal to this value here, index 1 is equal to this value here, index, and this goes on 32 times, index 31 is equal to this value here. As you can see, they're all below 2 to the power of 26. So why is that super important and it needs to be understood? Well, let's say you have index 0, right, and we have this value here. Well, as we mentioned earlier, we have calculated list R with all of these R values, right? So if this is the index, the first index returned, well, then you fetch that R value, right? So you fetch, in this case, R46131,392. And remember, as we previously discussed, when you're calculating R here, right, it's a 31 byte hash, and that is equal to this value, right? Because we're grabbing the value that the index is representing, which is 46131,392, and that was obviously created with the block height and the M value padding. So that should all make sense, because what you're doing here and what Autolykos is doing is that you're generating 32 indexes. Based on these indexes, you're fetching specific data from the dataset list R, and you're fetching 32 R values contained in list R given the indexes. So that's very important to understand, because now you understand why Ergo and Autolykos is memory hard, because it's fetching data from the memory, right? It's fetching that for every nonce, it's fetching 32 pieces of data from the memory. So in this case, it's memory limited, because you're limited on the speed at which you can fetch 32 pieces of data, which are R values in list R. So it is a little confusing. It did take me a really long time to wrap my head around all this, but hopefully this helps, and hopefully this diagram helps. I'll put it up somewhere. But that should make sense. So what you're doing here is you've completed line, so we're on line 8 now, and what line 8 does, as we mentioned here, you have to find 32 elements such that the hash of the sum of the elements is less than the target. So once you've fetched all of these R values stored in list R, you fetched 32 of them, you sum all of them up, and then you hash the sum, right? So this is just, line 8 is just summing all of the 32 values up, line 9 is hashing all of them, and if the hash is less than the target, much like in the other proof of work mining schemes, then you either succeed or fail with mining the block, right? And if you succeed, then you return M and nonce. These values are just returned to the network. If the other nodes see the block as being valid, then obviously the miner can be rewarded in Ergo. And there we have it. We basically covered all of the steps in block mining. And I think everything is pretty much, yeah, awesome. So I think there's just a couple of things I just want to mention and as to why Autolykos is like pretty awesome. The first is the memory fetches per nonce. So with Ethereum, we saw that every nonce, you have 64 mixes, 64 memory fetches per. So you basically have one memory fetch per hash, right, in Ethereum. In Autolykos, when you're actually doing the proof of work, you only have around 4 hash instances. One here, one here, one here, and one here. So at least 4, because this function can be looped. So you have at least 4 memory instances. You have at least 4 hash instances. So in this case, you have for Autolykos, you have at least 4 hashes, and you have 32 memory fetches, as we mentioned, right? So that's why, first of all, Autolykos is a lot more memory hard than Ethash, because you have much more memory utilization compared to the amount of hashing that the algorithm is doing. So that's awesome. But then you might have the question, well, what if we have hardware that increases the speed at which we can fetch memory? So for example, SRAM. SRAM is a type of RAM that can read and write really, really fast. The only downside is SRAM is expensive, right? And also it's not dense at all. So if you want to integrate a bunch of SRAM, you're going to take up a lot of space on the around the core, but you're also going to have to pay a lot. And then keep in mind that the data set just continues to increase. So if we're at a data set where we got 32 gigabytes of RAM that is required, we need a ton of SRAM. And at that point, it just won't even be feasible because it'll be so expensive. But it'll also start taking up parts around the core that are, electricity doesn't teleport. So the electricity will still have to travel a longer distance outwards to reach the memory. So it's really not that feasible to integrate SRAM and create sort of an SRAM ASIC, I guess you could call it. At least at this point, that's my thoughts. If you disagree or if you have any thoughts, I'm very happy to hear comments. Because if you have any thoughts on things I've mentioned wrongly or stuff like that, definitely happy to check comments on that. Because we live and learn. But that's the first point. And the second point is Blake 2B256. So the importance of Blake is, first of all, that it's incredibly fast. It's naturally fast. And the second thing is, it's somewhere in here, but basically Blake exploits features of modern CPUs, also including GPUs, stuff like parallelism, stuff like multiple cores. So Blake 2 already, as a function itself, integrates the hardware present in GPUs. So it's already sort of more optimized for GPUs than ASICs can make it themselves. And that is relative to other hash functions like SHA-256. So yeah, the benefits of Blake are that it's more hardware heavy and it's more optimized already for GPUs. So that's where I want to end it. Seems I've lost connection, but anyways, hopefully you enjoyed this video. Hopefully you learned something. Quite a lot we covered. So yeah, that's pretty much it, guys. If you made it this far, I'll buy you a beer at some point. But yeah, congrats, and hopefully it's all good. Peace, guys. Have a good one.